Let's take a look at day 4 homework. We've got 6 questions. A few of them are long. This is because we got some limiting reagent questions. Question number 1. Determine the amount of titanium metal produced when 2.8 moles of titanium chloride reacts with 5.4 moles of magnesium. So we know 2.8 moles of this and 5.4 moles of this. And we're asked how much of this. Now, it doesn't say a mass, it doesn't say what amount, so let's just say moles, because moles are easiest, right? So we have to figure out which one of these is in excess and which one of these is limiting. Now, since they're already in moles, we don't have to convert them to moles, but we have to do our pretend thing. Okay, so we have to do 2 columns. And I always wrote this in blue, so we're going to pretend TiCl4 is used up. Over here we're going to pretend Mg is all used. So we start off here on this side with our moles of TiCl4, which is 2.8. Then we're going to go to our moles. We're going to see how much Mg we're going to use. Using our molar ratio, it's 1 to 2. Okay, now we're going to get an answer here that's pretty easy. So how many moles Mg in 2.8 moles of TiCl4 if it's 2 to 1? There's our ratio. It's going to be 5.6. So to use up all of our titanium chloride, titanium 4 chloride, we need 5.6 moles of magnesium. Okay, so let's look at the other way. We're going to start with our moles of Mg, which is 5.4. We're going to see how many moles of TiCl4 we would need in order to use this up. So it's just going to be how many moles of TiCl4 for 5.4. And this one here is a 2 to 1 ratio. If we have 1 mole of TiCl4 for every 2 moles of Mg, 5.4 times 1 divided by 2 is 2.7. Okay, now going back to here, let's see what we actually have. Okay, so let's check. So I've got 2.8 moles of that. Do I have 5.6 moles of this? No, I don't. So TiCl4 is not our limiting reagent. It is in excess. Because I have 5.4 moles of Mg, and I have 2.7 moles of that. Good, so Mg is limiting. Good, so now we can use our magnesium to figure out how much titanium there is. So we're going to go from our moles of magnesium, which is 5.4. We're going to go to our moles of titanium. Titanium, using our molar ratio, it's 2 moles of magnesium to every 1 mole of titanium. So I do, how many moles of titanium will I get from 5.4 moles of magnesium if there's 1 mole of titanium for every 2 moles of magnesium? Simple as that. 5.4 times 1 divided by 2 is 2.7 moles. To the correct number of significant figures. All right, so that was an easy limiting reagent question. The next one is a hard, full-on limiting reagent question. You will get one of these questions on your test. I'm turning the page because it's going to take a page. You'll get one of these questions on your test, and you'll get a full page to do it on. Fortunately, we have the chemical reaction right here. Fe3O4 plus 4H2 gives us Fe3Fe plus 4H2O. What do we know? We got 100.0 grams of this, and we've got 10.0 grams of this, and we're asked to find out how much of that is made. And we're going to do this the full meal deal, so we're going to put grams. We also have to figure out how much excess reagent is left over. So we've got to convert both of these guys into moles first. That's our first step. Convert both of those guys into moles. Okay, so this is question 2. I start with my map. I've got my moles. I've got my mass of Fe3O4, 100.0 grams. Then I'm going to my moles of Fe3O4. And over on this side, I'm going to go from my mass of H2 all the way down to my moles of H2. My mass of H2 is 10.0 grams. All right, so let's get this started. How many moles of Fe3O4 are there in 100.0 grams? If 1 mole has, I sure hope I got a calculator somewhere. Oh boy. I think I got to go wandering off to find my calculator. All right, here we go, calculator. Let's just press clear. Ooh, that was my knee. So we got Fe, iron. And we've got Fe3O4, so iron is 55.933 times 3 plus O4 is 15.999 times 4. So 1 mole has 231.795 grams. So I do 100 divided by that number, and I get 0.431 moles. 142 moles. I'm keeping 5 significant figures. All right, now let's do the H2. How many moles in 10 grams? If 1 mole has 2.016 grams. So 10 divided by 2.016, 4.9603. That's 5 significant figures. Now we do our pretend. So here's our pretend line. All Fe3O4, and on this side we're going to do all H2. So we're going to start with our moles of Fe3O4, which was 0.43142, and we're going to figure out how much hydrogen it would take to react with that. And we're going to use our molar ratio from our, and our molar ratio is 1 mole of Fe3O4 add to 4 moles of that. So that's 1 to 4. Now over here we're going to start with our moles of H2, which is 4.9603. We're going to figure out how many moles of Fe3O4 we would use for that. Molar ratio here is 4 to 1. All right, so let's do these questions. I want a different colored pen. I want my pink pen here. So how many moles of H2 we get with 0.43142 if it's a 4 to 1 ratio of hydrogen on top, Fe3O4 on the bottom. So I take my 0.43 and I times it by 4. And I get 1.72 5 sig figs. This one, How many moles of Fe3O4 will there be? Will be needed to react 4.9603 moles of H2. If it's 1 mole of this to 4 moles of the hydrogen. So we do that 4.96, we divide that by 4. And we get 1.2401 to 5 sig figs. All right, now let's check to see what we have. Remember, these are our actual lines. This is how much we actually have. So, I'm going to choose this pen. Do I have this much iron? Yes, I have this much iron. Do I have this much H2? Yes, I have this much H2. That means Fe3O4 is limiting. Now let's look at this one. Do I have this much hydrogen? Yeah, I've got that much hydrogen. Do I have this much iron? Here's my actual amount. Here's my pretend amount. I do not. I've only got 0.43 in actuality, and I would need 1.24. This doesn't work. So H2 is in excess. So now we continue down our Fe3O4 side to figure out how much iron is produced. So we continue on with our map. So we go with our moles of Fe3O4, which is 0.43142, and I still have that stored in a memory in my calculator. And we're going to go to our moles of Fe using it's a 1 to 3 molar ratio. Then we're going to go from moles of Fe to our mass of Fe using the molar mass. All right, so let's do our first step. How many moles of Fe for 0.43142? If I've got 3 moles of Fe for every 1 mole of Fe3O2. So I do my 0.43142 times it by 3. And we're going to have 1.2942 moles of Fe. Right? It's just 3 times this amount. Now we do our molar mass. So how many grams of Fe will there be in 1.2942 moles? If there are 55.933 grams in 1 mole. 55.933 grams in 1 mole. So we take this times it by 55.933. And my final answer should be in 4 significant figures because I started out with 4 significant figures. 72.39 grams. That's my mass. Now let's see how much excess there is. So remember, our excess is equal to our total amount minus the amount used. Right, the total amount of hydrogen that we had 4.9603. 4.9603 moles. And we used up, according to this, we used 1.7257 moles. So we do our 4.9 and we subtract the 1.7257 to get a total of 3.2347. And this should, so 3.234 moles in excess. All right, now you could figure out the number of grams for that if you wanted to. We're just going to leave it as moles. You can use the molar mass to figure out the grams. It's not difficult. You just times this by 2.016. There you go. That's a full limiting reagent question with excess. Calculate the moles of the reactants. Pretend that you're using up each one and see how much of the other one you would use. Then see which one works. Use the limiting in the rest of your stoichiometry. find the excess. All right, number 3. Now that the limiting reagents is out of the way, let's get on to number 3. It's easy. Whew. Be plus 2HCl yields BeCl2 plus H2. My theoretical yield of beryllium chloride was 10.7 grams. If my actual yield was 4.5 grams, what is my percent yield? Well, right, percent yield is equal to your actual divided by your theoretical. And in this case, it is 4.5 divided by 10.7. 2 sig figs, 3 sig figs. Our final answer will have 2 sig figs. So 4.5 divided by 10.7. 42%. 0.42 or 42%. You can write it either way. Now it's number 3. Number 4. Here's my balanced chemical reaction. What's my theoretical yield of sodium oxide? That's this guy here. We don't know. We need it in grams. If I start with 20 grams of calcium oxide, so we got 20 grams of that. I did the experiment, get a 75% yield. How much was produced? So we got 2 questions. One, we have to figure out the theoretical yield, and then we have to figure out how much was actually produced. So let's build our map. We start off from mass of CaO. We go to moles of CaO. Sorry, mass of CaO is 20 grams. We're going to pretend it's 2 significant figures. Then for moles of CaO, then we're going to go to moles of Na2O. Na2O. Then from that, we're going to go to mass of Na2O. Right, there's our map. It is a 1-to-1 molar ratio, so we just have to, like, whatever we get there, we write down here. So, how many moles of CaO are in 20 grams? If 1 mole has, let's do CaO. Calcium is 40.078. Plus 15.999, 56.077. So 20 divided by that number, 0.3567. 0.3567. I'm going to write that down to here, 0.3567. Then we do this molar mass calculation. So how many grams are in how many grams of Na2O are there in 0.3567 moles? And we got to do Na2O, 22.990 times 2 plus 15.999, 61.979 grams in 1 mole. So we multiply it by that 0.35 number. It'd be 22 grams. There we go. So that's how much. I've got the full number in my calculator. Now we have to do the percent yield. We know we got a 75% yield, so we're trying to figure out how much sodium was produced. All right, so let's write out our formula for percent yield. Percent yield is equal to our actual divided by our theoretical. Our percent yield was 0.75, and we don't know our actual, and we know our theoretical is 22 grams. So we take our 22, multiply it by 0.75. I've got the full 22 in my calculator, so I times that by 0.75. 16.57 or 17 grams to 2 significant figures. So to get to my 75% yield, we would actually need 17 grams produced out of 22. There you go, that's question 4. Moving on. Question 5. How many grams of solid carbon will react with 826 grams of oxygen gas to produce carbon dioxide gas? So we've got to write out our chemical formula. Carbon plus oxygen gas gives us carbon dioxide gas. Pretty simple synthesis chemical reaction. It's 1, 1, 1. Perfect, nice, even molar ratios. We've got 826 grams of this guy. We're trying to figure out how much carbon we need. How many grams of carbon? So what we want to do is we want to try to make it so that this reaction has as little waste as possible. So we start out with our mass of O2, which is 826. 303 significant figures. We go to our moles of O2 using our molar mass. Then we're going to go to our moles of C using our molar ratio, which is simply 1 to 1. Then we're going to go to our mass of C using our molar ratio. First one, how many moles of O2 are there in 826 grams if 1 mole has 31.998 grams? Right, that's 15.999 times 2 is 31.998. So I do my 826 divided by that number, 25.814. Then I can just copy that down since it's a 1-to-1 molar ratio. 25.814 moles of carbon is what we need. Then we can do our last molar mass. How many grams of carbon will there be in 25.814 moles? If there is, carbon is just simple, 12.011 grams in 1 mole. So I take that answer, we times it by 12.011. 310 grams of carbon is needed. All right, now it's question number 5. Pretty basic. Question number 6. I hope I have enough space for 6. It's getting a little dicey. I've got 1.4 liters of a 0.250 molar solution of CuCl2 reacts with solid zinc to produce solid copper and aqueous zinc chloride. How many grams of zinc are required to react with the given copper 2 chloride? All right, so first we need a chemical reaction. So we got CuCl2. And that's in water reacting with solid zinc to give us solid copper and ZnCl2. Oh, beautiful, eh? Balanced. 1 Cu, 1 Cu, 2 Cls, 2 Cls, 1 Zn, 1 Zn, balance, 1, 1, 1. Now we have a concentration of this guy. We've got 1.4 liters at 0.25 moles per liter, or capital M. And we're trying to figure out how many grams of zinc will we need in order to make this reaction good. So this one, what we've got is a concentration. We go from our concentration to our moles. We got a concentration of CuCl2. We're going to go to our moles of CuCl2. Then we're going to go from moles of CuCl2 to our moles of Zn. Then we're going to go from our moles of Zn to our mass of Zn. Right now, this molar ratio is 1 to 1. So, okay, so remember, concentration is equal to our moles I'm going to have to do this work somewhere else. It's not going to fit in here. For a concentration, we've got 1.4 liters at 0.25 m. So I'm just going to work over here for the concentration. Concentration is equal to our number of moles per liter. All right, our concentration here is 0.25. It's equal to how many moles per 1.4 liters. It's 2 sig figs, 2 sig figs. Our answer for moles can have 2 sig figs. So we do 0. Times 1.4. 0.35 moles. All right, so we've got 0.35 moles of this. Copy that down because it's a 1-to-1 molar ratio, so we're going to need 0.35 moles of zinc. Then we can do our mass conversion. How many grams of zinc will there be in 0.35 moles? If there are, where's my zinky? 65.39 grams in 1 mole. So take a 0.35 times it by 65.39. And we get 23 grams, so the correct 2 significant figures. All right, so if we have this concentration of copper chloride, copper 2 chloride, then we're going to need this much zinc to try to react it as best we can with as little excess. All right, so there's all the answers. The answer to 6 is 23 grams. The answer to 5 is 310 grams. Let's go back. Let's look at the answer to 4. The answer to 4 is 22 grams theoretical, and then 17 grams of actual, giving a 75% yield. 3, 42% yield. Question number 2, we're going to do 72.39 grams of Fe with 3.234 moles of excess hydrogen gas. Question number 1, we're going to need 2.7 moles of titanium in our chemical reaction. All right, hope this was helpful. Hope you understand it. I hope you're catching on to the limiting reagent stuff. And thank you for watching.